Hello, everyone, and welcome to the Foundational Statistics for Forensic Toxicology webinar series. Throughout this series, we will hear from Sue Paring, Quality Manager with the San Francisco Office of the Chief Medical Examiner, and Aria McCall, Technical Lead with the Tarrant County Medical Examiner's Office. Today is Session 4, Use of Controls and Other Control Chart Elements. Without further delay, I will turn things over to our presenters.
So for today's detailed learning objectives, the attendants will understand the practical applications of the basic statistical compound or concepts throughout the examples. I'm going to hold just for 1 second, Sue, because it doesn't look like your slide is advancing. Yes, it is. Okay, so the attendants will understand control data and the information it can and cannot provide. And that really is going to be the bulk of our presentation today. And you're going to be able to distinguish between systematic and random variation. So remembering that method validation concept that I talked about in the first slide. So as we all know or will experience, the validation process is a rigorous and intended to prove up your new or modified method with the intended accuracy and precision in which to report valid results and expose any potential issues that may come up during testing. Because your final message in a method validation is going to be, this method is fit for its intended purpose, ... And it's when these criteria are met and we know about these particular issues that could affect our process. So during this talk and the various slides, I'd like you to keep in mind the question of what you are controlling for. Hold on 1 second. Looks like our slides are not advancing, Sue. So it looks like everyone's still looking at the first slide. There we go. There we go. Thank you, Vanessa, for that. So during the talk and the various slides, I'd like you to keep in mind the question of what you are controlling for. So ultimately, when you control chart, you're checking that your method is behaving in the same way that you originally validated for, right? So that's kind of the purpose for this whole control charting type of thing that we want you to kind of keep in mind as we're going through general examples. So just to harken back to my previous session, I have a little graphic for you that I want to just kind of give you a quick reminder of what we were talking about in session 1. So if you attended session 1, which I know you did, this is a graphic that is used to remind you of the terms that we use and how they relate to one another. So comparing the reference or target value relates to the accuracy, right? So inaccuracy, systematic error, and bias are all related to this umbrella of accuracy type of terms, whereas random error, variation, and the standard deviation are going to be relating back to our precision type data.
So in addition to these terms, we want you to remember the Alamo. Well, not really the Alamo, and it's not just because Aria lives in Texas, but I wanted a cue for us as we move through this presentation to be able to kind of trigger us to think back to these concepts. Not just the statistical concepts, but also the method validation concepts that Aria mentioned. Like she said, method validation is really to see if the method that you've developed, that you've inherited, that you read in a paper, that you borrowed from somebody else's lab, is fit for purpose, right? At the onset, before you put it into production, before you start using it. And that's the purpose of that, right? To determine that your method is ready for use. Whereas quality control is saying, like, is my method behaving? Does it continue to be fit for purpose? So you can think of this as a loose analogy of your method validation being your property line and your quality control being your fence line. Surely you're not going to set up your fence line to go beyond your property line, right? But where exactly you place your fence, how close to the property line, what shape the fence is somewhat up to you, the property owner, right? So during today's presentation, I'll flash this icon on the screen in a couple of places to remind you to remember the Alamo, to remember how the QCs in your fence line fits into the method of your property line. So what is the purpose of quality control? The purpose of quality control is simply to control the quality of the results that we produce, right? Pretty straightforward. First and foremost, at a granular level, it's simply, did my QC pass? Did my batch pass? Can I report these results, right? And if not, a laboratory's method or a laboratory's procedure will specify what to do. Maybe inspect the batch, inspect the reagents used. Maybe the results are simply reported qualitatively, or maybe some of the samples or all the samples are repeated for testing, right? But the benefits don't just stop there. Quality controls also allow you to monitor method performance of the method over time. And lastly, quality controls can provide you with gobs of valuable data from which you can glean useful information from, like how's the health of my column? Does it need a trim? Does it need a replacement? Right? This kind of information can be gleaned from some of the quality control data that we collect during the actual production of a method. But as the series is titled Foundational Statistics for Forensic Toxicology, we're going to focus on the statistics part of quality control and in quality control charts. So we'll start with a simple example to begin with. Let's say a laboratory prepares a custom quality control mix in methanol, and it's used by being spiked into whole blood and part of an assay. This assay has many, many drugs, but let's focus on one of these. And the target of this QC mix is 5 nanograms per mil. Right? This drug in this mix, the target is 5 nanograms per mil. And the control limits that the laboratory has set for this QC material is the classic target plus or minus 20% acceptance criterion. Well, 20% more than 5 nanograms per milliliter is 6%, less is 4 nanograms per milliliter, right? Pretty straightforward so far. So I'm going to remind you here to remember the Alamo and what is that all about. Now, you might remember that in ASB 036 and in method validation, and for this laboratory, their method validation plan said that the bias of this method could not exceed 20%, right? And so if you take the concept of bias, right, how different a value is from the target or the reference value, you can see that bias is easily visualized on a control chart in this way. Target is that purple line in the middle here. And if the value is below the target where the word bias is, it has a negative bias. And if it is above, right, then it's got a positive bias. Pretty straightforward. This chart shows this information seamlessly because the target is right there in front of you. So simple enough. Bias from method validation is reflected one-to-one by the control limit here. Both are 20%, right? The fence line is the same as the property line. They're one and the same. Super easy. We're off to a really good and simple start. So as data is being collected, this control chart starts to fill in. So it might start out looking something like this, where each batch's points are being populated one at a time. But again, I'm going to call you back to remember the Alamo. What about it? What's the other critical aspect of method validation that we often think of along with bias? You're saying precision to yourself out loud. You'd be right. That is what I'm after here. Precision is also able to be monitored through the use of control charts. And in what way? Notice precision here is in that black text, and here the black dots represent the data points that are collected right from each iteration of a QC being run. The spread, the precision, the dispersion, right? Remember these terms from session 2? The spread is easily visualized on a control chart as well. You can't really guess what the standard deviation is from visually looking at it, but you get a feel for if they're close together or if they're far apart. You can see some patterns, and you might see it might be narrower in some stretches or narrower in some control charts than in others. So visually, we get a general idea of this as well. Now, the precision or dispersion can be further detailed using statistical terms, right? It could be something like range. Remember, that's the max minus the min. So the full range of the values of the precision can be described. The mode or the mean, which we've talked a little bit about, or standard deviation or CV, which is the standard deviation divided by the mean. These are concepts that we covered in session 2, but also relevant as we're talking about the conglomeration of quality control data that might be collected over time. So whether precision is large like this, or if it's narrower like this, it's visible from your control chart, and the summary statistics that we learned about can provide additional information, a little bit more detail, right? But really, what are we talking about? The primary goal of quality control charts, right, and of quality controls is just immediate feedback for an individual QC, and whether the results from its corresponding batch are okay or not. Are they in control? Are they out of control? Are my results usable? And that's easily discerned and visualized quickly on such a control chart. You see that in the top here with that red marker. That point is clearly outside of the ranges marked by those yellow bands, that it's out of range, that there's something wrong with that one, and some inspection or qualitative reporting or something is going to be done, right, based on this laboratory's procedures. But beyond this, though, it's helpful to understand how the distance, how large the distance of points are away from the target is a reflection of bias, as we were talking about, whether in method validation or the ongoing performance of a method, or also known as systematic error, right? These concepts are interrelated. Bias and systematic error are describing how far away from the target or the expected concentration your results are. And similarly, the spread or dispersion of the data is a reflection of precision, or in other words, the random error that takes place during the performance of the method, whether it's during method validation or during the ongoing execution of a method, right? So those are the basics of control charts, not just the various components or elements of it, but also their connection to the specific method validation parameters, right? We're moving a little beyond just the individual batch acceptance. Did my QC pass? Are my results okay? To kind of a reflection of ongoing fitness for purpose. Oh, what? You want more? Yes, there's more. Yes, I never thought you'd ask for more statistics, but I think maybe what you want more of is guidance or guidelines. Yeah, and yes, there's that too. And this comes to us in the form of ASB 54, the standard for a quality control program in forensic toxicology laboratories. Published in 2021, the link is right here below, but not only does the link provide you a copy of the standard, but there's actually a fact sheet and a checklist that are quite useful tools as well as you kind of digest this information. Our discussion today is not exclusively on ASB 54, rather the general concepts, but this guidance does provide us quite a bit of information and some more details to help make our practices make a little more sense. So Aria?
Yes. So my section is going to be covering a little more about what the ASB 54 says. And just as Sue said, it's going to be given from the statistical angle. So a large part of learning statistics is that it plays a role in our laboratories as to what our guidelines are. So we all know, we all endeavor in our laboratories to do and demonstrate that our work is within the established guideline, or at the very least, mindful of them. So understanding the ASB standards with this statistical framework is something that we always want to have kind of in the back of our mind, essentially. So what does ASB 54 say? So all control results shall be recorded and monitored, including those that fail. So it's the phrase including those that fail. Sue, it looks like you popped over to the wrong slide. There we go. one before that. Including those that fail is what I want to spend a minute talking about. Your control charts should always include those data points that have failed, just as it states. But let's take a second to remember that not all data is good data. We want our control chart to reflect our overall assay performance. So there are some things that can be eliminated when doing calculations because they don't reflect that. A statistical definition of a, quote unquote outlier is an observation that lies in abnormal distance from other values you are evaluating. This works when you're studying a population and when summarizing it, you are considering whether or not a data point is representative or not. So in session 3, you may remember that Brigitte mentioned these as part of statistical tests that are available to you. However, when we're talking about control data, consider simply what data ought not to be included. And I'm talking about very simply. These are the type of outliers that I'm going to focus on. These are the data points that ought to be excluded from any kind of statistical analysis you're going to do on this data set. So rather than based on an abnormal distance, we're basing this assessment on basically known explanations. So let's go through some real world examples here. So controls that are valid to exclude. You drop your QC vial, right? It makes sense. If I drop a vial, I don't have data to add to my control chart. Adding a null result doesn't really add any value to a control chart and would ultimately be incorrect to include in my calculations if I'm trying to do a calculation for, say, average or mean or standard deviation. A null result doesn't really give us any value here. So what's another example? So let's say you used the wrong pipette volume for your QC, or you missed this tube when you're spiking internal standard, right? Because missing a tube when you have 100 of them in front of you just never happens, right? I mean, again, knowing that it's an erroneous value doesn't give you any insight into the working nature of your assay. In our next example, what we have is you use the wrong solution. So you use the wrong QC, because they're all pretty much created in the same size, color, volume of vial. They're all similarly labeled. They all use the same font, so why would we accidentally grab the wrong QC? So I'm not saying anything about whether or not you would be able to actually report anything at this point, just whether it would be proper to enter a result when you have nothing. Those aren't calculations that you want to be, that isn't data that you want to be using your calculations on, essentially. And then for our last criteria, it's a failed curve criteria. So let's think about this for a minute. So if you have a curve that failed, would that produce a QC that you would normally report? Or would that produce data or quantitative data that you would report? Probably not. A failed curve isn't going to give you good quantitative data. So the QC can't be expected to give results that are indicative of an assay performance. It makes sense, right? Essentially, you're going to have other issues at this point, right? Your curve didn't pass. Now you've got a whole thing you got to do to look into that. So I still want to make it clear that's not to say that some of these types of excluded data don't have some type of value, but to include them in calculations for, say, the mean or 2 sigma would not be helpful, and it will not reflect correctly when calculating something like, say, for the measurement uncertainty. So it's a very logical process in general. It just becomes important to remember, as we have said previously, what are you controlling for, right? We want to harken back to that method validation again. So moving on, ASB, and this is about your positive controls and your process control limits. And we're just going to go through this very simply. So target-based control limits shall be based on method validation requirements for bias. So for example, plus or minus 20% of the target or calculated mean value. Control limits shall not exceed the maximum allowable bias as established in, guess what? The method validation for that particular assay. So remember in the beginning how we said things relate back to the validation plan? A plus or minus 20% acceptance criteria was established there, and that theme is continued as you enter your QC data for assays. Our next slide is going to be a visual example of this in a control chart. Now we've already seen this. Sue has already shown this to us as a very simple example of a control. I've just added some very simple stats up in the upper corner. So we have the prep target, as she has said, and then our limits of plus or minus 20%. So very simple. So moving on to the other type of limits we can use. So a statistical evaluation with warning limits of a mean plus or minus 2 standard deviation and control limits, which is the mean plus or minus 3 standard deviations, shall be calculated based on historical control data. So Sue is going to be diving into this a little bit more in the next section, but remember, I just want to make this very simple. The guidelines refer to either of these methods, a plus or minus 20% or a 3 standard deviation being utilized. So the next slide is going to revisit this concept with this 3SD visualized in an example that you're going to see later. And just so everyone knows, I'm underlining trend here. I haven't seen a lot of questions pop up yet. I'm hoping for more. I haven't forgotten about trends. I'm going to ask about them. That is one of my main questions, and we're going to cover it. So don't be worried. So let's see our example of mean with 3 standard deviations. And here it is. So basically, this is a different representation of the data that you're going to get a chance to look at. You saw a brief look at it earlier, essentially, of the spread of data in here with a mean that has been calculated. It's a little bit lower than the target of 5, with a 3 standard deviation control limits visualized here. So at this point, I want to get everyone going, and I have a poll for you. So I'm curious as to what your laboratory uses as your QC limits for ethanol, and if it's listed here. So do you use a target? Maybe you have a 0.08, that's plus or minus 10%. Maybe you have a target, which is your 0.08 as an example, plus or minus 20%. Or are you calculating out a mean using 10%, or a mean using 2 standard deviation, or 3 standard deviation? And if you click other, I'm just curious, maybe you can pop into the chat and say what the other option is here. Maybe I forgot to list a different way to do it. And if it is, then please let us know what that is. We're just going to give you a couple of minutes while I get a sip of water and see what kind of results we get. Looks like Tiffany uses 5%, target plus 5%. That's great. 3%. Wow. Okay. Yep. Ethanol is certainly one of those types of assays that can be very tightly controlled. Target plus 5, target plus 5. You guys are basically telling me I should have put plus or minus 5. I get it. That's fantastic. 3%. Okay, target plus or minus 5, whichever is greater. I like it. That's excellent. We all love ethanol because it gives us really beautiful control charts. I mean, they're just really tight grouping in there, right? Unlike some of our other drugs. Okay, let's take a look as to what our polling results kind of came in at. It looks like plus or minus 5 is probably going to be up there too. Other. Okay. Yeah, plus or minus 5. Thank you, guys. I forgot to include that, but you are correct. A plus or minus 5 for ethanol would be perfectly viable as well. So thank you for your participation. Don't go far. I've got another question for you and another polling question. So on my next slide, we have what does your lab use as QC limits for non-ethanol? So we know you have varied assays and everything has its own behavior. So feel free to select multiple things. If you've got, one that's a plus or minus 20%, and then you do a mean for something else, go right ahead. I think in our lab, we've got a target plus or minus 20% for sure, and some standard deviations as well. Again, if you have some other for non-ethanol that's not listed here, please let us know. It's fantastic. I'm reading some of the others that we had in here previously. These are great. Thank you, Melissa. I like it. It looks like I did better on polling question 2 because there's not a lot of people putting in their others for this particular one. So target plus or minus 3 standard deviation. Okay, thank you, Gail. All right, let's take a look and see what we got. Target plus or minus 20%. Yep, that's pretty much where we lie as well. For I don't know what everyone's reasoning is for that. I mean, it's definitely simpler, right? And isn't that just enough of a reason to do it? So as we wrap up this polling question, we'll see if Sue has any comments about it, and she's going to take over the next section as we go into statistical control limits.
Great, thanks, Aria. Thanks for bearing with me with the tech issues I'm having over here. So we'll see how this goes with trying a different setup. It'd be interesting, Aria, maybe if we can for session 6, look at what these are side by side. I wish I had time to put them together so we can share it with them share it with everyone side by side. But it is kind of interesting, and I'd be curious to see how laboratories have thought through those differences, if it's different for ethanol versus non-ethanol, especially if one is significantly wider than the other. So thanks for your participation there. And we're gonna just move right on into what are these statistical control limits about? Based on the non-ethanol poll, there's still about 73% of folks that are using Target, and absolutely nothing wrong with that necessarily. There's, it's definitely a viable control limit option. It's presented in ASB 054, and there's nothing wrong with it, but I do want to highlight and just help folks understand the statistical control limits and what we might want to watch out for in both of these scenarios. So Aria briefly introduced the 2 types that we just talked about in ASB 54, right? The target-based control limits, for example, plus or minus 20% from the target concentration, or plus or minus 5%, or whatever that might be. And then the statistical evaluation ones, where the center of this control limit is the mean of some historical data. And the range, or the acceptable plus or minus, might be 3 standard deviations from the mean. Many people use 2. 3 is also mentioned in ASB 54, so we're using this in our example here. And in this graphic, they do seem really similar. So I don't want to mislead you that they're always going to be about the same. But I do think it's an interesting example to show side by side when this might happen. And in this situation, you can see that the mean of the historical control data, that dark blue line right above the word mean in dark blue, is pretty close to the target in that purple line, right? And further, the CV of this data set is really small. It's actually about 6%. And so 3 standard deviations at 6% CV is about 18%, which is why it's so similar to the 20% that we see in yellow, right? So it's in this particular example that they're quite similar because the precision, the CV is really narrow for this compound or this QC. The mean is quite close to the target. So they're centered similarly, and the ranges at 3SD and at plus or minus 20% are also fairly similar. But that's not always the case, right? If you've done this before and you've tried to plot these different control chart limits to see how it might affect your data, you may have found that some are really not this similar. Some of them are very similar. So what do we need to know about these two options? And what do we need to know about them to use them appropriately? As we discussed earlier, target-based control limits seamlessly reflect bias, right? It's simply part of that range determination. It is the center, right? And also with that comes really simple math. Plus or minus 20%, you can do it on the back of a napkin, you can do it quickly and maybe even in your head, right? But when might it not make sense to use a target plus or minus 20%? Now, in the example of ethanol, as we learned from the poll question, some of you guys did put your reasoning in there. And yeah, there's plenty of reason not to. And I'm thinking just in terms of when the data, what does the data tell you? And when might your data be telling you, hey, this is not appropriate? Not because of some external guidelines or anything, but just what does the data actually say? This is best seen through an example. So let's say laboratory, like the first example, set the control limits to target plus or minus 20%. They collect data and looking back at it, it's really tight. There's not a lot of dispersion. The spread is pretty narrow. The precision is quite small. This is awesome, right? This is what you want to see. You want to see a super precise method. It is nice to see, but notice the gap between the actual data and the control limits. Both above and below the data, the black data points there, there's quite a big gap between that and the yellow line. So if you ran a QC and you got this result here, would you say that the method is in control and that it's behaving as it should be? Probably not. The rest of your data is much tighter than that, and that seems to be a bit out of line. So the limits here are really too broad for the actual precision of this method. There wasn't an issue with validation, right? The precision passed and all that. That's why we're using it. But for monitoring ongoing fitness for purpose, the limit is too broad or it's too lax to be able to detect or to alert you if it is behaving out of control. So this is my warning, right? For target-based control limits, while bias is natively reflected, right there in the title, target is reflecting the bias. But where precision is tight, the range may be too broad, right? And this can be accounted for, this can be assessed by visually inspecting the limits in the QC data that we generated as we did in the previous slide. It gives us a really easy visual, a really quick assessment to see if the range makes sense given the actual performance of the method. And remember that method validation, while the precision may have been set with a certain range for validation, the actual performance is different, right? You're collecting real data. You're not saying like, is it above or below that? You're saying, well, what is it actually, right? It's not whether or not it met a threshold. It's what does the data actually tell you? So pivoting to statistics-based control limits, bias is not natively reflected, right? Target is not part of that control range. It's not part of that control chart, and it does require specific math. So I wouldn't say it's complex math because throughout the series, we've given you some tools and some knowledge and a lot of references with which you can easily calculate mean and standard deviation, right? This data is being collected in a spreadsheet or a workbook. That data is available and you can calculate these things to make up the elements of this control chart, but rather that it's specific math because it's specific to the data that has been collected. It's specific to the control data that you're using to generate these limits. So visually, what does that look like? Aria showed you this slide earlier where the mean is the center of this and plus or minus 3 standard deviations is also plotted. And just like for target-based control limits, precision is visible, right? Based on the actual spread of the data, whether it's large or narrow, precision is easily seen on a graphical representation. But where is bias, right? Where target ranges had it straight in there and automatically built in. One way to visualize this is to just add it onto the control chart. You could put the target line, I've left it here purple, but also as a dotted line to show that it's not the center of the control limit and the control range that we've established. But a visual representation of this allows us to continue to monitor its fitness for purpose as the method is taking place. So while bias is built in or inbuilt to target-based control limits, precision is inbuilt to stats-based control limits, right? Standard deviations are a reflection of precision, whereas the target, right, is part of that calculation for bias. And so while in the target-based control limits, we need to do the additional work to assess the standard deviation, check the precision to make sure that it is fit for purpose and it continues to be fit for purpose. In the statistical evaluation, where you have a mean plus or minus 3 standard deviation, my reminder to you is to assess bias, right? To make sure that continues to be fit for purpose. And I'll give you an example here to help us visualize the importance of this. Let's say a laboratory prepares a QC material, let's call it lot X, and the target was indeed 5. The laboratory prepares it, and before putting it into use, they've selected a mean plus or minus 3 standard deviation control range. So they've got to collect some data to figure out, well, what does that mean and what is the standard deviation? They collect the data, and this is what they find, that the mean of the 20 replicates is around 4, and the range ends up being around, 3.4 something to 4.6 something. And what do you immediately notice? You notice that the whole thing is below the target, right? There's a negative bias where all the results obtained were below the target concentration of 5 nanograms per mil. And even at that expanded range, it doesn't even cover the intended nominal concentration. So is this reflecting a method bias? This method wouldn't be in production if it hadn't been through validation. So the laboratory may easily rule that out. But then they might be asking themselves, was the QC prepared incorrectly? Was this drug spiked into lot X at too low of a volume, so the resulting concentration is only 4 rather than 5 nanograms per milliliter? And if you're thinking, but what if the calibrators were prepared incorrectly? You may also be onto something. In toxicology laboratories, many of us are preparing both our calibrators and quality control material in-house. They might use different vendors and different sources of certified reference material, but they're both being prepared in-house. So when you see a bias, is the QC wrong? Is the calibrator wrong? Are they both wrong? How do you know? And so while target-based limits automatically reflect bias and thus additional assessment of standard deviation or CV is needed, right? Stats-based limits do not natively reflect bias. They do, however, reflect precision through standard deviation being part of that equation. So for statistical-based limits, an additional assessment of bias is necessary. And that leads us to this concept of, well, what do we do with all that, right? There's some benefits to these things. There's a caveat that I have mentioned. And I want to give us a little bit of guidance, just really broad stroke to understand, well, what do we do with that? What are we meant to do? We have these two options. There's additional work required in both. And these are the things I want you to consider. First is your knowledge base, whether you individually, if you're responsible for this, or that of your laboratory, is do you understand these concepts? Do the concepts of bias, standard deviation, CV, of whichever model you're using, whichever option you choose, does it make sense to you? Do you understand it front to back, back to front? And what is the application? As we saw with the ethanol poll, sometimes the application really directs a narrower control limit for us, right? Even within target-based control limits, you could select a 10% versus a 20% or a 5%, right? And the application may drive it. Now, even with where the application requires it, you've got to make sure that the data makes sense, right? You have the right starting material, you have good enough CRM, or the process is robust enough and precise enough to provide that kind of um, to be able to match that kind of control limit. But both knowledge base and application are critical parts of this decision-making process. Can you explain the monitoring process? Do you understand how it is monitoring your fitness for purpose as an ongoing reflection of your method? And can you justify the selection that you've made and explain the justification? So Aria, we'll jump back to you as
All
we
right,
continue our discussion.
sure. So, a large part of learning statistics is that it plays a role in our lab. So, we're just going to continue on with our ASB standards and discuss a little bit about our control chart. And does our control chart really cover it? Next slide. There we go. So, in section 12, this is about monitoring our quality control data. So we shall have a procedure for monitoring and recording quality control data, and it should include these elements. All controls charts should be recorded, monitored, including those that fail. So we have a control chart, and we're including the ones that fail, not necessarily the ones that are, what we call like a bad data, like we have no data for it. You certainly can include those in your control chart, just to be clear. I saw a quick question on that. You can include them in your control chart. You're just going to have an extra step when you're going to crunch your statistics in which you don't want to include those particular null datas, essentially. And in B, we have where applicable, monitoring will include the statistical evaluation of data using spreadsheets, calculators, whatever you can do. And as a quick note, again, we should all know the statistical evaluation can be anything from averages and mean all the way to hypothesis testing for variation in your individual staff members or instruments. And then we have the two big ones. Where applicable, control data shall be plotted in a manner that will allow for the detection and evaluation of trends and identified trends that could negatively impact the validity of results. So a lot more underlining here, and let's get to it. So what is a trend? So why do we monitor for a trend? How do we monitor for a trend? What do we do with them? Like, these are some of my basic questions about trends. And let me tell you what I came up with. So let's talk about the why first. So remember our lens of method validation. A method validation starts and ends in a relatively small amount of time, at least small in comparison as to how long we want to continue using this particular method, right? And during that validation timeframe, which let's just say anywhere from 1 to 3 months, the number of variables is somewhat limited despite attempting to introduce as many as we can as part of the validation. There is one variable we can't really account for, which is a passage of a significant amount of time. So your validation may only have one lot number prep that you used for a calibration or for a control. You may only use one mobile phase prep or one column lot. The passage of time allows for more of these kinds of variables, including your instrument robustness, to be assessed. So that assessment can take place with your control chart, right? You can look for trends that can give you hints or clues or data that tell you about your instrument robustness or your lot robustness, essentially. So is there any other reason we would monitor for a trend, or how is your lab monitoring for trends? Let us know in the chat. How are you guys doing it? So essentially, now we've covered the why. We have that method validation lens. We know how we're going to do it. We're going to make control charts. But now what? What to do with it? What to do? And do I actually have to do something about a trend? Or do I just have to know about it? The language in the ASB, just says trends. It doesn't have any specific parameters essentially around it. So you have a control chart. We understand why, but now what? So I'm going to bring Sue in for a little bit of discussion here. And so do I actually have to do something about a trend, or is it okay to just know about it? If I know my drug declines over time and my control chart reflects this, as long as I know when I need to create a new control and I understand the risks, is that okay?
Yeah. Are we still following the guideline given that response, right?
Right.
So I'm going to direct us back to your previous slide, really, is ASB 54, where .c talks about, yes, you have to be able to do it, right? You have to be monitoring for it to know that it's happened, right? You've got to do it so you can see it. Once you see it, then what? And that's pointed out in .point D here. It's not just any identified trends have to be addressed. It's any identified trends that could negatively impact the validity of the results shall be formally addressed and documented. Right. But I want to make it really clear that, you can't just say, well, they are not going to negatively impact them. How would you know? Right. First, you have to see them. Then you have to understand what might be causing them. So in the example that you gave, Aria, I think, you see a trend, you know what's happening, you have a plan for it. A plan is actually being done. And it's not even that it may be formally addressed or documented. You actually have a proactive practice in place, and you're just observing what you expect to see.
Gotcha. Okay, so I want to go through a little bit of an example of what I would do essentially as a regular analyst, a person in my laboratory, if there was a trend that I did see. Maybe it's not something as simple as flawed; it's something like unidentifiable. And I want to take you through a little bit of the assessment that I make about it, essentially as a regular day-to-day kind of activity, right? You pretty much have three options, stop, caution, go. So if it's trending up or down, what do I do? What risks am I taking if I run it again? So if your risk is high, the worst thing we can do is put out inaccurate results. We're all scientists. No one wants to do that. So maybe we stop running until there's a resolution. If one QC goes out, I may test multiple QCs next before I start running actual cases where I have a limited specimen, just kind of test it out, see what's happening, see if that was something that happened one time or if there's something that's going to continue to happen, or I do nothing. One failed control isn't going to make me, shut down the labs and turn out the lights and send everyone home. So I take no action and we just carry on to see what happens next, essentially. So, the notification or noticing a trend doesn't mean, your hair's on fire and things have to happen, but, you have some choices to make at that time. You can do nothing, monitor, use some caution, or just wait until the next one and see if it actually becomes a trend. At least that's what we do in our lab in particular.
That's great, Aria. This is what we were we were joking about. Don't use a fire hose to blow out a candle, right? Just because there is a trend, right? And you saw some of the data that we showed. How do you know if there's 2 points it makes a line? Of course, it makes a line. That's the definition of a line is the connection between 2 points, right? But that doesn't mean you stop everything and run around like a chicken with its head cut off. So to kind of tie up what we talked about, the do's and don'ts of quality control charts, I want to summarize this for you, right? First and foremost, they do indicate what's out. That's really, really the simple, most primary function of control charting and why we have control limits to prevent us from, like Arya said, reporting results that we don't intend to, that are not reliable. They do allow for trend monitoring. So you have to be monitoring for it to be able to detect it, and you have to understand it to know what to do about it. And thirdly, it does show for random errors. It does show our random errors on there, the spread of data, the precision, that random error is easily visible. But it does not show everything, right? The examples that Arya gave of data that should not be included for subsequent calculations, if they're not being included on your control chart at all, not just excluded from your calculations, they have to be monitored elsewhere. This is part of a quality assurance program that quality control charts may not be the end all be all, the only place where things are recorded when things go wrong. So whether it's a drop vial or a wrong solution or failed curve, right? If it's not being recorded in control charts, there needs to be a home for those things so that they are being monitored. What we were trying to say is that it's not necessarily appropriate to be including them here where you're going to be using that quantitative data to summarize using statistics, right? That's not the data that's of interest here. And lastly, just to remind us that there are other mechanisms for monitoring. Like I mentioned, these things that go wrong, there has to be other homes for them, other ways to record them, other logs, an instrument log. And there's many, many other mechanisms for monitoring. We participate in proficiency testing. There's other mechanisms like that that's programmatic and lab-wide that help us give feedback on the work that we're doing to help ensure the quality maintains really high.
Okay, so I'm going to roll through these next three slides pretty quickly. And so I thought this was an interesting thought exercise, which is that what has the failed QC ever told us besides we can't report, right? I mean, in the moment you're analyzing your set and you're discovered that your QC has failed, what does it do? What does it tell you? Well, I can tell you one thing it tells you, you're going to be sitting at that instrument a lot longer than you had originally planned for, right? So so you have a single point of data that has failed. Does it tell you anything about how your method is performing? Well, maybe, but more data becomes more powerful, right? So I have the purpose of quality control. Sue talked about this earlier. I'm not going to beat everybody up with it again, but I want to emphasize the everyday analyst importance. Ultimately, you're left with a failed QC. And you've done all the usual testing to make sure it's integrated right, all of the things it injected, the pump didn't fail, all of that stuff. But ultimately you have a failed QC and probably some repeat testing in your future. So unless fortune smiled upon you and you can re-inject. But I want people to understand that your QC contribution as a bench level chemist, coming in for the grind to get out samples, your QC contribution of that batch or set that you're trying to report every day becomes part of a greater picture. And once in that greater picture, it becomes a lot more powerful. So when you add that into an Excel sheet or into any kind of control charting type of thing, you get the opportunity to do like many other things that Sue talked about in points 2 and 3. So you can monitor performance, you can glean feedback, and you can see that power in your control chart. So as we close, just remember, even if only one poor soul in your laboratories has the primary responsibility for reviewing control charts or running stats on them, your everyday benchtop work gives them the numbers, the data that hopefully you have a better understanding of now, for them to make larger lab-wide decisions. Sue, do you have anything before we wrap up? I know there's at least a couple of questions in the Q&A we should probably hit.
Yeah, no, that's great. Thank you.
All right, excellent. I think we have an additional reading page, and then we can get to some Q&A.
Oh yeah, definitely not references, but just some fun reading if this topic tickles you, some interesting things. I saw a quick mention in the chat somewhere about Westgard also. We can talk a little bit about that in Q&A. If we run out of time, we'll talk about it in session 6. The concept of quality control and qualitative analysis is really interesting to me. So there's just some fun things. I was going to list it as additional summer reading, but I realized people watching the recording, it might not be summer by the time they get to it. Just some fun things that we like to talk about.
Catherine Bollinger at RTI, and we'll get into the Q&A. So if you have any questions, go ahead and put them in there. So one of the first ones that we have was back early in the presentation when we were talking about bad data and if it failed. I think it was more of a clarification of if bad data is excluded, which it failed, then should it be recorded under ASB 054?
Well, for me, I think the intent of the ASB standard is, that you're not excluding good data, but that it has happened to fail. I don't think it adds any value for a dropped QC. We all have our own internal procedures in order to, deal with when those types of things happen. But I think what we're talking about here is not like a known reasoned outlier. We're talking about regular, just as a part of the process, failed QC, and those should be recorded. Sue, would you agree with that?
Yeah, definitely. Another way to say that is just to say you don't exclude it just because it failed. We're not scrubbing the data that we're only including QCs that passed. It's that unless there's a known reason, like the ones Aria talked about, that's not a comprehensive list, but just like an identified reason why it's not a good data point to include. Just because it failed does not mean we,
Okay. Thank you, Sue and Aria. The next one is when we were talking about more of the trend data and you had the polls pop up. Someone commented that we tend to use a percent range for forensic data and then a standard deviation divided by CV for clinical data in our tox lab. And I think this question kind of goes into, the next part of that was if using standard deviation and CV, are you covering the Westgard rules? And I know
Yeah,
that's come
interesting
up
question.
twice.
Yeah, I don't know if the attendee is still online. I'd love to hear why that difference, right? Why percent range for forensic data and why something different or standard deviations for clinical? Is it something about the process that drives that? Is it more historical practices or tradition, for lack of better words? Or is there a theoretical concept? So if you're still online, whoever asked that, please put that in the chat. I'd love to hear from you. In the additional reading, you noticed Westgard was one of those, and I've dug into this some over the last couple of years. And Westgard rules has its place in has its home really out of clinical chemistry and clinical toxicology. How that translates to forensic toxicology, I think, is a question that is worth exploring. And while it's available in a lot of clinical QC monitoring software and systems, the actual context for it, the reasoning why, and why it's set up that way, I think is worth looking into before we just take it and then slap it on to the work that we do. Um, I I think we're in a place in our field where a lot of that is still being discussed, and how much we deviate from clinical toxicology is still being understood and being explored. And you kind of see that in the reflection of the standards that are being put forth for forensic toxicology.
Okay. Thank you. The only other one we'll have right now is asking about a template Excel file for quality control logs. If you have one, you had a participant asking about it, that might be something that can be discussed in session 6 a little more if there is a Excel template
Yeah,
that you have.
I don't. We use a software called LabLink to help plot and visualize all that. Aria?
Yeah, so we are Excel. We still generate a lot of our control charts in Excel. We've recently bought a third-party statistical package that I am still trying to learn what all of the buttons actually do. So hopefully we'll be integrating that in a little bit more as time allows to learn it, essentially.
All right. Well, thank you, Sue and Aria, for the great presentation today in our session 4. And if everyone wants to be back on session 5, that will be on July 11th, where we'll talk about calculations of type A data from control data for measurement uncertainty. So have a great rest of your day.
Thank you.
Thanks, everyone.
As you depart, we kindly ask that you take a minute or two to complete our post-event questionnaire. The link will be pasted in the chat and also appear as you exit the Zoom room. Your feedback helps us improve our outreach efforts and continue to provide the best experience possible. Thank you again for attending, and we hope everyone has a great day.